So in our last target, we talked about reflection in mirrors. We talked about flat mirrors and we talked about curved mirrors. In this next target here, we are going to talk about refraction in lenses. Okay, so in this lesson here today, we're going to talk about refraction. We'll talk about what's called the index of refraction. We'll talk about Snells Law. In the next lesson after this, we'll go ahead and talk about lenses, and we'll draw some ray diagrams for lenses. But today, refraction, and our target is to be able to explain refractions in lenses. So let's go ahead and talk about refraction. Okay, to kind of understand refraction, you have to think about the speed of light for a minute. Okay, light always moves at the same speed. If you remember, the speed of light is about 3 times 10 to the 8 meters per second. Light always moves at that speed. And one kind of issue I take with textbooks sometimes is they will describe the speed of light as slowing down when it moves through some kind of medium, like when it moves through the air or when it moves through the water or something. They say that light slows down. And I really wish they would be a little bit more clear about that, because it's not actually the speed of light that's slowing down. It's when light moves through a thing, what happens is the light will be absorbed and re-emitted by atoms, and there's some little delay. When the light is moving between the atoms, it's moving the speed of light, but there's some little delay as it gets absorbed and re-emitted by atoms, right? So the average speed of light through some medium is lower than the speed of light, right? So does that make sense? Its average speed is lower. And you really have to think about the speed of light there to understand refraction, because the effect that has is when light moves from one medium into another medium, that change in speed is going to cause it to bend, right? Cause it to go in a different direction, right? And that's what refraction is. So like you can see in the picture, probably everybody's seen a glass with a straw in it. And, right where the break in the water is, right where the top of the water is, it looks like the straw is broken, right? And this is refraction. This is just the bending of the light due to the different mediums, the light moving from the water into the air. Okay. Every different material will affect the path of a beam of light differently. Okay. Each different kind of material has what's called an index of refraction. And the index of refraction is really just kind of a number that tells us how much that material will kind of bend light, sort of, right? Okay. The index of refraction is just a number. It doesn't really have a unit, and the lowest index of refraction is going to be 1. So the index of refraction of just an empty vacuum is exactly 1. And we have a chart here, and this chart will show you the index of refraction for some different materials. So like air has a very slightly higher index of refraction than vacuum. It's 1.0003, right? And if you look on there, water is about 1.33. And you can look at some of the other materials on there. Glass is 1.52. There's some different materials on there. This chart will be helpful when you do your assignment. And you can find it in the slideshow that's on the Google Classroom, right? The index of refraction, when we talk about the index of refraction, we use a lowercase n for index of refraction. And you can calculate it by taking the speed of light divided by the speed of light in that medium, right? So n equals c over v. Here's a fun little trick using the index of refraction, right? I have 2 materials here. I have glycerin, and I have a beaker made out of Pyrex glass. And glycerin and Pyrex glass have just about the same index of refraction. So if you look here, and I ask you, can you see the beaker? You would probably say, yeah, I can see the beaker. And then I say to you, can you see the other beaker? Can you see the other beaker? See the other beaker? Because they have just about this, because it has just about the same index of refraction as the glycerin it's submerged in, you really can't see it. It's invisible. And you might be saying, oh, maybe you can do the same trick with water. here's a beaker inside of some water, right? I mean, you can really kind of obviously see it in there. It's really much harder to see this one. Kind of a neat trick. Okay, if we know the different materials that a beam of light is traveling through, if we know the material that it's coming out of and the material that it's going into, we can predict what path it's going to take when it meets the boundary between those two materials. We can predict how the light's going to bend. And I'm going to put a diagram right up here. And what you're going to see is usually what we'll do is we will put the space on top of the diagram for the material that it's coming out of. And the space on the bottom is the material it's going into. And then we'll draw in that diagram a normal line, a line that's perpendicular to the boundary, right? It's called a normal line. And we can draw the ray of light as it's coming in at a particular angle to that normal line. We'll call that the angle of incidence, right? And then we can use, there is an equation we can use called Snell's Law that will help us figure out what angle it will refract at. So then below the boundary, we can see the angle of refraction. We can see the angle that it bends to. Now, when light moves into a medium with a smaller index, it will bend away from the normal line. So the angle of refraction will be larger than the angle of incidence. When it moves into a medium with a larger index, it will bend towards the normal line. So that angle of refraction will get smaller than the angle of incidence, right? So the example that you can see here in this particular diagram that I have up there, the angle of refraction is smaller than the angle of incidence, so that we can conclude that the index of refraction of that medium is lower than the one that it came out of. That said, we can predict exactly what the angle will be using Snell's Law. Here I'm going to put Snell's Law up there. It says n1 sine theta 1 equals n2 sine theta 2. And n1 and n2 are the two indices of refraction, right? So n1 is the index of the medium it's coming out of. N2 is the index of the medium it's going into. And then theta 1 would be that angle of incidence, and theta 2 would be that angle of refraction, right? So we can do n1 sine theta 1 equals n2 sine theta 2. We can predict that angle of refraction. Let's go take a look at an example of how to do that. Okay, the example here, it says a ray of light traveling from air into glass strikes the surface of an angle at an angle of 30 degrees. At what angle will it be refracted? Okay. Well, it might be nice to draw a little diagram. It might not be absolutely necessary, but let's draw a little diagram and see what this is going to kind of look like. So here I'm going to draw the boundary between the two materials, and it said that it's coming from air into glass. So up here we have air, and down here we have glass. Okay, let me take down the problem there, and let me put back up that little chart that tells me the indices of refraction of different materials, and then we can look up what is the index for air and what is the index for glass. Okay, and we can see up there the index for air is 1.0003. And for glass, it is 1.52. Okay. And it says that the angle of incidence, it's going to come in at 30 degrees. So here is my ray of light. Well, let me draw my normal line first. Here is my light. It's coming in at 30 degrees. How is it going to go away? Well, I can see that it's going into a material with a higher index of refraction, so it should end up coming out at a lower angle. But let's figure out exactly what that angle is going to be. We'll use Snell's Law to do that, what we just talked about. So Snell's Law says that n1 times the sine of theta 1 equals n2 times the sine of theta 2. Okay. N1, we have the index for air is 1.0003 times the sine of theta 1, which is 30 degrees, equals n2, which is 1.52, times the sine of theta 2, which is that angle that we're looking for. Okay, let me grab my calculator. Well, we can solve this a little bit first. I'm going to divide both sides by 1.52. So 1.0003 times the sine of 30 divided by 1.52 would equal the sine of theta 2. And then if you remember your trigonometry, we want to get that theta all by itself. So to undo that sine, we'll have to do the sine inverse. So when I have that theta 2 by itself, I'll end up doing the sine inverse of all of this right here. 1.0003 sine of 30 divided by 1.52. And now I'll grab my calculator and see what that works out to. So I'm doing the sine inverse. Let's see, I've got 1.0003 times the sine of 30 divided by 1.52. There I get about, get about 19. So theta 2 should be about 19 degrees. So that angle right there, about 19 degrees, which is consistent with what we thought it was going to be. We thought it was going to be less than the angle of incidence, and we did in fact get less than the angle of incidence. So there we go. Not too terribly difficult, huh? So there is some fun stuff about refraction and the index of refraction and Snell's Law. Good stuff there. Next time we'll talk about lenses. So hopefully that helps us to be able to predict and explain refraction in lenses. So until then, take it easy.